Hello everyone, we are Summit Builders, Illinois' leading general contracting firm. Our key team members are Suresh, Anam, Harshal, Kanchan, Robin, and Morris. We are a team of experienced project engineers, project managers, and cost estimators. We specialize in high quality educational buildings with a keen eye for energy efficiency, sustainability, and high end finishes. It is an honor to be working on a project for this prestigious U of I's ECE building. The ECE building is going to be a space for high-tech learning and collaboration. The building is about 230,000 square feet located on 306 North Wright Street of Urbana. The project duration is about 4 years and the budget is about $95 million. The user is going to be the Department of Electrical and Computer Engineering. The ECE building site is located in one of the most central location of the university town, that is Northcott, with Beckman Institute to its north and Nanotechnology Lab building to its south. The site has its main entrance from the North Wright Street, and the east side of the site has a huge open lawn area, and it has a pedestrian street on all four sides.
The main purpose of this construction project presentation is to provide clear guidance and instructions to the on-site construction team. It outlines what needs to be built for the new electrical and computer engineering building, specifying the structure's design down to component level. The presentation also outlines how each building aspect should be constructed, including the order and sequence of the various construction activities. Key details covered include the types of materials and equipment to be used at each stage. The objective of this construction project is to deliver the new electrical and computer engineering building safely, on time, and on budget. Safety is the top priority, with the goal of ensuring no accidents occur during the build. The structure must also be completed as designed, meeting all architectural and engineering specifications. It is critically important that each construction phase is finished according to the scheduled timeline. Careful planning and resource management will be key to staying on track.
During construction and development projects, it is indeed important to mark a side boundary, which is typically larger than the property boundary. The red light in the picture indicates the side boundary, which is encircling 4 pedestrian walking sides around the building and almost half of the ground behind the building. Signages plays an important role in information and safety. There are 3 types of signages being used on this site for public. Those are sidewalk closed, site under construction, and informatory signs.
The major impact of construction would be for pedestrians. The area is actively used by pedestrian traffic, which will get affected due to closing of sidewalk in the west of the site. Taking away few portions of the construction boundary in the east side of the site in the quad is also going to restrict the pedestrian traffic. The red lines in the left diagram shows the regular pedestrian movement before the construction, and the blue area marked in the right diagram will be the closed sidewalk areas when the construction begins. The pedestrian will be diverted through crossings as marked by red arrow. The north pedestrian walkway is accessible while the south walkway is blocked and included as a part of site boundary for construction. There will not be much impact on vehicular movement as there is generous number of gates to the site, which will not impact the regular vehicle movement due to trucks and site work. A stop or a construction warning sign can be implemented to control the speed of vehicles, consequently helping with the safety of public.
To efficiently manage operations during construction, we'll set up temporary field offices and storage areas. 4 gates will be installed, 2 for vehicles and 2 for personnel. Initially, field offices will be located on the south side to oversee excavation and foundation work. Once the structure is up, offices can be relocated inside. The staging location for materials will be on the east side for easy truck access. This area will serve as a temporary storage zone during deliveries and material handling. We have created different areas for offices, storage, and site access to ensure that operations are well organized during this important initial phase of construction. To smoothly transport materials on and off-site, we've designated specific loading and unloading zones near the staging areas. These temporary locations will allow deliveries to be efficiently received and routed where needed. The open area in front of the building is well suited for bulk materials like concrete, which won't be stored long term. By planning in advance where trucks can pull up to unload, we can avoid bottlenecks and keep the flow of deliveries on schedule.
The possible truck route has been tracked from a potential supplier, that's the prayer material supplier. In the figure, the truck can move from the West Springfield Avenue to the South County Fair Drive and then onto the West University Avenue and the South Wright Street before entering the site. The University Avenue towards the north of the site can be considered for all the potential truck access, as this road has no overpass of 11 feet 10 inches, which can be observed in the West Springfield Avenue towards the south.
In addition to the standard site preparation work needed, this project requires a couple of extra steps. We will need to obtain a permit from the university as our site boundaries extend into the North Quad area. Erecting a secure perimeter fence will also be crucial given the site's proximity to a major street. This fence will help control access for both security and privacy reasons during construction. With these additional preparations in place, we'll be ready to start the excavation and site work phase of the project.
Identifying utilities is one of the most important activities before performing excavation. We call JULI to identify utilities. JULI stands for Joint Utility Locating Information for Excavators. JULI is a not-for-profit corporation that provides contractors, excavators, homeowners, and others who may be disturbing the earth with a free service phone number to call for the locating and marking of underground utility facilities. JULI uses the following color coding to locate specific utilities: red for electricity, yellow for gas and oil lines, blue for water, orange for communication, and so on. We have also listed the owners and their contacts for each utility, and we need to contact them before disturbing any of these lines. As you can see in this slide, we have also indicated the utility locations on the site demo drawings.
Site clearing is a crucial first phase in the construction project. We are assuming obstacles and vegetations on the site which need to be cleared off, and the equipment used for it are excavator, loader, and dump truck.
Site demolition is one of the important steps before you start the construction process. When the site was investigated based on historic data and existing site conditions, it was found that no demolition was required before the starting of construction, except the clearing of few peripheral trees and vegetations.
Indeed, excavation and site work for the University of Illinois Electrical and Computer Engineering Building, various specialized equipments are crucial for efficiency, safety, and precision. These equipments are as follows. The excavators would be used for digging and earth removal. The bulldozers are vital for terrain leveling and shaping. The backhoes would provide precise digging and trenching capabilities. The loaders would be used to move the materials on the site. The dump trucks would be essential for soil and debris transport. The surveying tools would provide total station and GPS for accurate measurements. Lastly, the safety gears would provide equipment to ensure a safe working environment.
Phasing in excavation is an important step for efficient and effective construction flow. Building construction is divided in two areas, Area A and Area B, as the north and south plus central wings, respectively. The order of excavation is determined based on accessibility for excavator and trucks and manpower. The efficient zone to start the excavation is from the northwest corner of the building Area A, and consequently following the building footprint to enter in Area B. The last point of excavation shall be the northwest corner of the south wing, that is the northwest corner of Area B. The excavator and truck positions are marked in the following diagrams along with the direction and area of excavation. For increasing productivity rate and reducing the time of excavation cycle, the excavation is divided into two phases, Phase 1 and Phase 2. Phase 1 excavation depth is 10 feet, followed by Phase 2, which is 20 feet of excavation depth. For this purpose, along the timeline of start of Area B excavation, in Phase 1, a slope has to be constructed in order to start the excavation of Area A in Phase 2. The following timeline figure shows the scheduling of these phases with respect to their areas. Consequently, when the Area A excavation of 20 feet is completed, the foundation excavation phase of Area A can begin, while Area B Phase 2 excavation is still undergo. Based on the calculation of approximate volume and the workflow as assumed based on the timeline, number of excavators that would be operational at a time would be 2.
Now that excavation is complete, it's time to remove the heavy equipment used in this critical early phase. First, operators will clean and inspect each machine to ensure it's in good condition for transport. Excavators, dozers, backhoes, and other large vehicles will need to be safely loaded onto trucks. Once the site area is cleared of debris, it will be left in a clean state, ready for the next stage of foundation work. Properly demobilizing excavation gear is important for construction to smoothly transition and keep the job site safe and organized. The foundation system has different types of footings, such as square, combined, and continuous. These footings are designed to accommodate various soil conditions and structural loads. Footings will range in size from 5 feet to over 15 feet and depths of 18 to 44 inches. With rebar reinforcement, grade beams, and a 5 to 8 inch thick slab on grade are also part of the design.
During this phase, in addition to equipment from the site building and excavation phase, we employ tools to fortify the foundation. These include the trench boxes that would be used for ensuring worker safety, the formwork that would be used for crafting molds for concrete foundation using wood or steel forms, the concrete finishing tools that would be used for achieving a polished surface. The concrete mixtures would be used for mixing and transporting concrete for the foundation. In addition to that, the concrete pumps would effectively be helpful in placing concrete in large areas. Lastly, the vibrators would be essential for consolidating and compacting freshly poured concrete, ensuring its strength.
Foundation phasing will take place based on the area divisions. Let's call the foundation of Area A as Phase A and foundation of Area B as Phase B. Location and accessibility of equipments will differ based on phases. On the start of Phase A, the Area B excavation would still be undergoing. Hence, the central zone between the buildings would be under the use for excavation, dumping, and hauling. Hence, in Phase A, the Gate 1 will be utilized for access of concrete pump, and the red hatched area along the north periphery of the site will be used as a potential location for concrete pump and mixer truck. For Phase A, the steel rebar staging area would be the northeast corner of the site, marked in yellow. When moving to Phase B, The central portion of the site shall be utilized for concrete mixer and pump trucks, and the steel rebar staging area will be moved more to the south along the east boundary as marked in purple color. For this phase, Gate 2 will be used as the primary gate for truck movements.
Here is the calculations we performed to measure quantity of concrete required for foundations. We first identified spread footings, which include square footings and combined footings. As shown in the details, we also identified continuous walls, continuous footings and slab on grade. The total concrete we would need is about 3,800 CY. Based on the calculations, we came to a conclusion that we would require about 380 concrete mixers of 10 CY capacity, and the concrete will be poured component by component phase wise. That is, first we'll be pouring the foundations and slab on grade and walls for phase A, and then for the phase 2.
After completing the foundation construction, the large excavators and bulldozers will be loaded onto transport trucks. Backhoes, loaders, and dump trucks previously used for moving materials will also be loaded onto trucks. Cranes will lift and secure heavy trench boxes and concrete forms for the next project. Smaller tools will be manually packed, and the site will be readied for the next phase of work. Steel framing forms the main structure by supporting beams, columns, girders, and trusses that span between the foundation and floors. The structural plans show the layout and dimensions of these elements to transfer loads down through the building. Coordination with other building systems is also vital, as equipment and openings may impact the steel framework.
After performing detailed superstructure analysis and our expertise, we have listed the following equipment requirements. Lattice boom crawler crane to lift heavy weights such as columns, truck mounted telescopic cranes because it can maneuver around the site easily and to lift lighter weights, concrete pumper truck to pour concrete for floorings, concrete trucks equipped with rotating drum mixers which continuously churn and mix concrete to ensure concrete remains in a workable state, mass climbing platform for a safe and controllable platform for workers to reach to the elevated heights, concrete forms for shaping and supporting the concrete during pouring, safety net for the safety of the workers on higher levels.
Superstructure is divided into three phases. Phase 1 includes structural steel frame, in which lattice boom is used for the erection of the steel columns and telescopic roller crane is used to erect beam, girder and metal decking. Phase 2 consists of metal decking and concrete pouring for flooring, which is done by laying out, securing and creating opening for the decking, preparing, pouring, vibration and compaction with finishes and curing. In phase 3, the structural steel erection and concrete pouring for roof is taken out with the help of cranes, and then column installation, beam installation, truss installation, bracing and bolting, and finally formwork, reinforcement and concrete pouring process. This slide indicates the placing of crane. Crane can be placed anywhere in the marked area depending on the requirement.
We have devised a plan for erecting the steel in the superstructure. Our approach is to start from the lowest level and progress upwards one level at a time. We will begin by erecting steel in the north wing, moving from west to east. After completing that side, we will then proceed to the south wing. Erect steel from east to west. This phased strategy, starting from the lowest level and systematically progressing across each wing, aims to prioritize safety and efficiency throughout the steel erection process.
The superstructure demobilization would begin with first looking at all the safety precautions and site evaluations, disconnecting the utilities such as gas, water, and electricity. The formwork would be removed by using cranes or hands based on the necessity of the situation. Then we would address the local laws and regulations for environmental considerations, finally inspecting the site from the plans. The different equipments such as the cranes would be first dismantled from the boom and the counterweight driven out and secured from the site. Then, moving forward to concrete finishing tools, we would simply pick the tools by our hands, pack them, and keep it in a secured position for future use. Similar to the concrete finishing tools, the formwork and the mast climbing platform would be stored and followed with the necessary systematic process kept in a secured place for future use. Lastly, the scissor lifts would be lowered, disconnecting the power and driven from the site in a secured way.
Mechanical systems are essential components in modern building for maintaining air quality, inside temperature, energy efficiency and safety. We are using three mechanical systems in our project. Those are heating system, ventilation system and temperature control system. The heating system used in the building is known as hydronic radiant heating system. This system uses warm water through network of pipe installed beneath the floor for heating. This system has many mechanical components such as trench, wall box, blank of panel, utility support, chilled water branch, etc. The ventilation system used in the building is known as HVAC system, where HVAC stands for heating, ventilation and air conditioning. This system uses hot and cold water for heating and cooling respectively. Some of the main components and connections which are used in this system are trench air box, round duct tape connection, fire and smoke dumper, goosenecks, fume hood fans, etc. Temperature control system installed in building uses water-based system to regulate indoor temperature effectively. These systems utilize water to either heat or cool indoor spaces, ensuring comfort and energy efficiency. There are several components used in this building such as chilled water system, cooling water loop, vacuum pump, clean water system, fan coil, domestic CIRC pump, etc.
Coordinating the mechanical systems in a complex building like this is crucial. We need to plan chase routes for ventilation ductwork that don't interfere with other trades. The layout of heating pipes and air ducts also requires alignment with structural elements to allow access and space. Placement of control panels, sensors, and wiring for temperature regulation needs consideration for accessibility and future access to penetrations. These are the main types of equipment we will use for our mechanical installation work on the job site during the construction process. Crane lifting equipment to lift and position heavy air handling units and other large equipment. Scissor lifts for accessing overhead areas to install ductwork, grills, sensors, etc. Forklifts to move large duct sections, equipment, materials, and supplies around the site. Man lifts for vertical access between floors during construction. Welding machines needed to join sheet metal duct sections during fabrication and installation. Pipe threaders to cut and join steel piping as required. Carts, dollies to transport equipment and materials within the building.
The installation process of heating systems involves several steps. such as design and planning, boiler installation, piping installation, coil placement, thermostat and controls, and finally testing and balancing.
The HVAC installation will be phased floor by floor, starting from the lowest level. Ductwork and equipment will be installed level by level to allow crews to work efficiently. Next, the north wing will have its equipment installed, followed by the south wing. The tasks will be organized according to the trade, starting with the installation of ductwork, followed by fitting and insulating. It's important to run electrical wiring before mechanical work is finished. The air handling unit, fan and controls will be installed first to allow for testing before occupancy. Startup and commissioning will occur per floor and zone after each area's installation is complete, from the first to fifth floors and finally the penthouse. After completing mechanical works, a careful demobilization process begins. We'll inspect and remove protective equipment, survey work areas, and review plans to ensure all components are accounted for. Utilities like gas, water, and electricity will be safely disconnected. Materials will be hand removed or lifted by crane if heavy. Waste disposal is guided by environmental regulations. A final inspection ensures that the site is completely clean and ready. Heavy machinery will be prepared for transport with dismantled booms and secured components. The demobilization concludes safely and efficiently, adhering to protective measures and an organized process.
Foundation to any successful project is efficient and effective electrical coordination, which ensures a working, safe, energy-efficient environment, and that our clients' needs are met. ECEB has a thorough network of electrical systems which has to be efficiently handled and coordinated to achieve the output as proposed. And as a contractor who is in charge of electrical coordination in this building, we make sure that electrical systems are designed and installed efficiently. Distribution of electric power, lighting, safety precautions, and adherence to construction requirements are all included in this. We are committed to maintaining the highest standards of quality, compliance, and sustainability, contributing to the advancement of cutting-edge technology and innovation in the field of electrical engineering and beyond. Our goal is to facilitate the seamless integration of power, lighting, and advanced technologies, fostering an environment that empowers both students and faculty to excel their pursuits. The systems that were identified were main electrical systems and backup electrical systems. While doing the floor-wise investigation of design, several electrical systems were identified on each level. For example, site level has electric manhole, duct bank, pole bases, plaza lighting, and generator pad. The basement level has lighting, electric room. The upper floors are mostly lighting, in which the fourth floor has an elevator machine room. Several kinds of lighting fixtures were also taken into consideration, taking into account the phasing of fixtures with respect to exterior and interior construction phases. Few electrical installation notes are listed here for your reference. More light to the components. Some of the main components as mentioned and marked are electrical manhole, duct bank, pole base, lighting, circuit breaker, transformer, distribution panel, magnetic starters, switch gears, conduits, cable, junction boxes, and some of the backup components are generator and solar panels. In the following slide, more details for electrical component is documented and planned in the form of figures. Looking into the distribution components on each level, an electric room suffices the requirement. The electric room is situated at the corner of the building and there are two in one wing. The electrical room has a panel, a distribution panel, and a busway. All these lead the conduits to the respective power output. Here were the pre-planning and investigatory slides for data required for the next step of planning. upcoming portion for the electrical details will be covered by my colleague Harshit.
Phasing the systems during different stages of construction would be a critical step to ensure smooth functioning of the electrical systems. In phase 3, that is during the excavation process, it's important that we would dug the duct banks and the generator pads along with the excavation. In phase 4, that is during the foundation and the substructures, we would emphasize on developing the temporary electrical lines for construction needs. Some of the conduits would be embedded in the floor slab of the basement. In the phase 5, that is during the superstructure, the conduits and the electrical connecting lines would be embedded and casted in the floor slab. Lastly, moving forward into the exterior and interior finishes, which is still under investigation, we would look to have the facade lights for walls, interior work like switchboards, electrical sockets and fixtures would be completed in this phase. A phase systematic approach was followed, starting with planning and permissions, then preparing infrastructure, wiring connections, and finally thorough testing and documentation to ensure a safe, robust electrical installation. The phasing plan for the installation of electrical systems shall be as follows. First, install electrical wiring and equipment floor by floor, starting from the lowest level and allowing the crew to work in progressing building areas. Install equipments in the north wing and then the south wing. Organize tasks by trade, example, electrical wiring to be finished before mechanical systems are installed. Tasks like installing lighting fixtures after interior finishing work and work subjected to damage. Stage 1 addresses the initial temporary setup. Stage 2 looks at the primary wiring. Stage 3 looks at the systems before finishing the work, which includes the temporary lighting, switches, temperature control, which can be finished in one day. Stage 4 looks at the final permanent installation, which includes the electrical system. These includes electrical system, HVAC systems, switchboards, fan, lights and outlets. Following equipments would be necessary during different phases of construction for smooth electrical coordination. The lattice boom cranes would be used for heavy equipments for lifting heavy loads. The concrete pump and the mixer truck would be essential for the generator pads and duct bank construction, facilitating concrete placement. Additionally, a scissor lift would be used to transport vertical elements such as conduits and fixtures to higher areas within the construction site. Smaller equipments would be required for electrical fittings. These would include equipments which help to hold and pull the wires together, such as the T-stripper and the cable puller. Further, drilling machines would be needed to drill holes in the wall. The long nose piler would help to grip, bend and cut the wire in tight spaces. The wire lead caddy would help to transport and dispense wire reels. The fish tape would help to thread and pull electrical wires through the conduits and the wall. Lastly, we would require different voltage testers, multimeters and circuit finders to detect, diagnose and locate and identify electrical circuits in the building.
This examination explores the component of ECEB building in terms of exterior cladding. The cladding in roofing demonstrates a deliberate approach to insulation and solar radiation management. The terracotta envelopment, covered in unique terracotta materials, makes a substantial contribution to insulation by utilizing a rain screen mechanism. A metal canopy with adjustable slats control the amount of solar radiation maximizing energy efficiency. Terracotta baguettes and sunshades have a dual function of increasing the visual appeal of windows and offering protection against solar radiation. The white roof, which reflects light, effectively maintains thermal efficiency with an R30 rating. This demonstrates a dedication to conserving energy and enhancing the building's sustainability and visual attractiveness via architectural refinement.
The following are the necessary equipments that would be required for phase 6, which includes exterior cladding and roofing. First, we would require scaffolding and access equipments which would be used to access the elevated areas. Then we would require lifting equipment such as cranes or hoist for lifting heavy loads. Power tools such as drills, saws and screws would be used for cutting and fastening the materials. Then we would use material handling equipment such as forklift or conveyor systems. Then welding equipments would be used for metal components. Lastly, we would use weather protection equipments and safety nets to protect the.
Here is the elevation of southwest entrance of the building, which has metal panel cladding. Using section number 5 and detail number 6, we can see that firstly, moisture protection fluid is applied and air barrier membrane is attached to the substructure, that is a concrete masonry wall, and then clips and brackets are fastened to the substructure, after which the panels are aligned and secured within the brackets. The joints are sealed using sealants or gaskets to prevent water infiltration.
For the granite installation, we will see the following figures that will detail the West Terracotta Labs. This is depicted in 8 in the drawing, which will also help explain the installation of the granite panels. Within this drawing, as we can see, we will look at the detail 7, 5.3.1 specifically, which will depict the granite panel attached to the substructure. For the terracotta panel installation, we will look at the following figures that depicts the southwest entrance wall, and is depicted in the drawing as a 3, which this helps us explain the installation of the terracotta panels. Within this drawing, we look for detail 4, more specifically 4.3.2, which depicts the terracotta panel attached to the substructure, and we also look at a more detailed view in detail 9, more specifically 5.1.3, which depicts the terracotta panels in a more detailed way in the substructure.
A detailed quantity takeoff was performed using Bluebeam, and we calculated exterior material for north and south elevations. From the calculations, we can see that dark red terracotta is the most used material across the elevations, followed by dark grey granite, light grey terracotta, and medium grey granite, and glass for glazing.
This slide outlines a 5-phase plan for completing the exterior enclosure and roofing of the ECE building project. Phase 1 will install the granite cladding system at ground level. Then, start installing terracotta panels on the lower levels, moving from east to west. Phase 2 continues the terracotta up the walls and adds aluminum panel installation to the mid-levels on the south and west sides. Phase 3 completes the terracotta wall installation and further progresses the aluminum panels. It begins with the aluminum curtain wall on the south side. Phase 4 finishes the aluminum panel and curtain wall work, installs terracotta for the penthouse, and adds terracotta and stone parapet copings. The final phase, Phase 5, installs terracotta baguette and accent trim systems, adds roof edge metal flashing and counter flashing as needed, and completes all sealant joints and accessories. This phasing approach methodically works from the ground up and allows trades to efficiently install exterior materials while minimizing disruption as the project progresses towards completion.
Demobilization of cladding consists of several steps, such as facing plan for demobilization, taking stock and categorizing based on usability and necessity, dismantling structure, cleaning and sorting of material based on their reusability and recycling. Pack and labeling material for transportation and storing, arranging transportation for the material and equipment, storing material in an organized manner for the further use, maintenance check on tools and machinery, maintaining code of demobilization activities, and finally reviewing demobilization process and feedback from the team. Analysis of framing and interior finishes. For base and floor, several finishes such as ceramic tile, straight rubber base, granite base, carpet tiles, and rubber sheets are used. For ceiling, finishes such as aquatic tile, granite board painting, gunmetal panel, and linear wood ceilings are used. For wall, the finishes such as low viscous paint, epoxy paint, granite wall panel, terracotta panel, and linear wood panels are used.
A wide range of interior walls are used in this building, and the most commonly used wall is the concrete masonry unit wall. And here are the few details of drywalls used in the building. Gypsum board used for drywalls is 5 by 8 inch thick throughout the project, and the aluminium studs are 25 gauge and are of varying thicknesses based on the height of the walls. Here's the quantity takeoff performed to calculate the lengths of interior walls. The values highlighted in orange are drywalls or CMU attached with acoustic drywalls. For basement, drywall quantity is about 297.76 linear feet and about 224 studs are required. For the first floor, including A and B part, drywall is 581.34 linear feet and about 437 studs are required. For the second floor, phase A, drywall is 1028 linear feet and about 772 studs are required. And for the fifth floor, A phase, drywall is about 1078 linear feet and 809 studs are required.
To ensure the successful construction of the new ECE building, a range of specialized equipment will be employed for both framing and interior finishing tasks. Drywall cranes and lifts can be used to install drywall on high ceilings, making it easier and faster to construct a 69-foot auditorium space. Scissor lifts and boom lifts reaching heights of 80 feet will give workers safe access to framing of bulkheads and soffits. Man lifts are essential for safely transporting personnel and materials to elevated areas. Forklifts will move drywall, lumber, and other heavy materials needed for framing. Carts and dollies will help transport tools and supplies throughout the building's interior spaces during finishing. We need this array of lifting and positioning equipment to finish the framing and interior construction of the new ECE building within the set time and budget.
In the framing and interior finishes, each stage is executed meticulously with collaborative efforts and regular inspections maintaining high quality standards. The team is committed to promptly addressing any concerns for seamless and successful project completion. During the initial phase, referred to as Preparation Phase 1, the goal is to evaluate and authorize offers for interior framing and finishing work. This encompasses acquiring requisite permits and authorization while assuring the enforcement for safety protocols and preparedness to the site. Transitioning to Phase 2, which focuses on interior framing, the goal is to commence the building of door and window opening as well as walls. This stage also encompasses the incorporation of electrical and plumbing systems with a particular emphasis on strict compliance with building regulations. In preliminary carpentry phase 3, The objective is to carry out the installation of sheathing and subflooring, construct interior walls, and create necessary structural elements. All supplementary essential duties are also accomplished during this phase, known as installation of preliminary mechanical and electrical components, involves the integration of electric and plumbing system into the building's framework, ensuring precise placement of HVAC system and actively seeking cooperation with other professionals to avoid conflicts. In following stage known as evaluation or phase 5, the focus is on organizing inspections for electrical plumbing and frame tasks. Any discovered issues or adjustments are swiftly resolved during this period. Proceeding to phase 6, referred to as an insulation. The objective is to affix insulation materials onto ceiling and walls. Unwavering compliance with construction specifications and the maximization of energy efficiency are of utmost importance in this stage. The goal of step 7, mounting drywall, is to effectively and securely install drywalls in interior areas, ensuring the surfaces are ready for future finishes and painting. Phase 8, interior finishing, encompasses the installation of windows, doors, and trims, as well as the application of paint or other wall coverings and the installation of flooring materials. During phase 9, final inspections, the primary goal is to do comprehensive inspections in order to confirm adherence to building codes. All outstanding concerns or shortcomings are resolved and required approvals for the final use of the property are secured. Phase 10 finalization is dedicated to systematic arrangement and preparation of interior space for practical usage. The methodical advancement guarantees a thorough and triumphant culmination of the project interior construction endeavor.
For the superstructure demobilization, we will have all the equipment in the superstructure phase getting out of the construction. So for all the equipment, the drywall, cranes and lifts, the scissor lifts, the boom lifts, the man lifts and forklifts, and also the forklifts individually, we will all dealt with the same way. We will drive them, mount them in the trucks, and secure them out safely of the construction.